Okay, I will just start, no?
Yeah.
Good. So this is the second lecture of our project. Today I split the lecture into two parts. I will in first part tell you a little bit about conditioning of branching processes. First on having a fixed progeny, a fixed size, and then conditioning critical branching processes on survival forever. In the second part, I would like to introduce you to the basics of electrical networks and all we need in order to be able to calculate the probability that the edge belongs to the uniform spanning tree. Okay, I start with the branching processes. I think this is an object everybody is very familiar with. We start with a probability distribution on N0, which is considered to be the offspring distribution. And that means that we assume that we have a root, an ancestor who has a random number of children according to this distribution. And given that we have built the tree up to the, let's say, age generation, each of the individuals in the age generation produces offspring again according to this offspring distribution independently. And this allows us, if we think about G as the random family tree, as an object in locally finite rooted trees, to uniquely determine its law by giving the probabilities that the restriction to the generation age gives me a tree which is restricted to generation A as just the product over all the vertices in the restricted tree, and we multiply the probability that the vertex V has CV of T number of children. This gives us the explicit law, and we are mostly interested for the project and the Poisson branching tree. For the Poisson branching tree, that means that you have a Poisson offspring distribution and you get a very explicit expression for the law of the Poisson tree with intensity mu. Okay, so if I want to condition on the total progeny to be n, there's a very classical tool by now how to do this. You usually use something which is called the Lukasiewicz walk, and it works as follows. You start with your finite tree and you order all the vertices in lexicographic order. These are these numbers 1, 1, 1. No, 1, 1 is the first child of the root, and so on. And then you traverse this tree according to the, you do it not like I pointed, but according to the lexicographic order as this one, then the second child of the first child, then the first child of the second child of the first child, and this one, and so on. And the way we are doing this is that you build a random process or just a kind of process by adding to your current position the number of children minus 1. So that means if I start in the root has 2 children, I go up by 1. Then I'm in the next vertex, has 3 children, I go up by 2. In particular, it means that if I'm in a leaf which has 0 children, then I actually go down. And you can also see something in that picture already. And this is broken now. I don't know what to do. Okay. You see that the first time that you come down to the negative is precisely the population size. And this is something which one can prove. But first of all, let's say that the red process you are seeing here, the so-called Lukasiewicz walk, is a random walk which has a jump distribution, which is just a shifted offspring distribution because we are always adding the number of children minus 1. Yes. Good. And what you see is that the first time you fall down to minus infinity is actually the time when you have discovered all of the vertices. So therefore, you get that the probability that the total progeny is n is just the probability that you stay non-negative. And for the first time, you are in minus 1 at time n. And there's a nice observation by Dwas, which might remind you to the reflection principle of a random walk. It's based on cyclic permutations, which tells us that if I have a random walk, if I have IID random variables, the distribution is just a shifted offspring distribution, then the probability that the random walks will stay non-negative and only hit minus 1 the first time equals 1 over n times the probability of the last value being minus 1. And this is quite nice because this allows you that you can identify the probability distribution of the total progeny with such a quantity. And in particular, if you shift a bit and you take now the jumps to be precisely the offspring distribution, then it means that the probability that the total progeny is n equals 1 over n times the probability that Sn is n minus 1. And as I said, we are mostly interested in the Poisson tree. So for the Poisson tree with Poisson offspring distribution, the random walk itself has also Poisson distribution, but with n times the original parameter mu. And if you plug in what I just told you, you get the distribution which looks like this. And it's not very common, but it's known in the combinatorial literature as the Borel distribution with parameter mu. Okay, and then we have everything we need in order to show what I claimed in earlier talks, namely that the conditioned Poisson tree, conditioned on total progeny, has the same distribution as a uniform tree. And in order to state this precisely, one has to be a bit careful because the uniform tree is not just the graph theoretical tree, which we had before with vertices and edges, but it's a combinatorial object, and we have to say what we count, and as the same tree and not. And for that, I introduced two spaces, the one of labeled, unordered, unrooted trees, and the one of rooted, ordered, unlabeled trees. And the reason is because the uniform spanning tree of the complete graph, which we were interested in, is an object which is labeled, which is unordered and unrooted. On the other hand, the Poisson one branching family tree, conditioned on total progeny n, will be an object which has a root, which has an order, but which is not labeled. And in order to make these two comparable in one statement, one needs a map which sends an element of t tilde into t by forgetting the root and the ordering, and then choosing a labeling, and we do this by default in a uniform way. And we have this, then one can formulate Aldo's result from 91 precisely. It works for any intensity mu. If G is the Poisson mu branching tree, and I take a tree which is labeled, unordered, unrooted, then the probability that after this procedure of forgetting the root and the ordering, but introducing a labeling, it equals T, given that the total progeny is n, is just the uniform distribution on the space tau n. No? I have here a small calculation. You can do this when you are at home and you would like to know, but we have everything we need because we introduced the probability distribution of the tree G, and we introduced the distribution of the total progeny. So it's a very elementary calculation to do this. What can I do? Okay, I'll be more patient then. Are there questions so far? Say again, No, with the, you forget about the root. You don't need the root. You want unrooted. The spanning tree is usually unrooted. And
so Anita, if there are questions, maybe you can just repeat it.
Okay, that's a good point. Yeah. From now on. Okay, so then there is the spine decomposition we have talked about, and this appears if we are now conditioning on survival forever. And this is something I also would like to explain a bit. We have our branching tree, and we are interested in the law conditioned on survival. And you know, this had forgotten a little bit. Let me see. We should be here now. So for explaining this, I associate the branching tree with actually the branching process set from which it comes. And I do two assumptions. First of all, I assume that we are conditioning on an event of probability 0. That is that the branching tree is in the regime where it's going to die out almost surely. And secondly, as a technical condition, I need that the probability that I'm alive at time n minus k for a fixed k has the same asymptotic behavior as the probability that I'm alive at generation n. No? This is quite technical. It is always satisfied if we are in a critical regime and if we have finite variance. Good. If we do this, we can just by simplification manipulation of the condition probability reverse the event on which we condition, and the other one, we find this kind of formula, and we can evaluate this one, the probability that given that I know the tree up to generation k, that I'm still alive at a late generation N, expressed through inclusion and exclusion. No? First of all, you want that there exists a leaf which is still alive. You can say you can sum over all the leaves, but then you have overcounting because there might be 2 leaves, no, which are still alive, and so on. And using such an inclusion exclusion and using this assumption, you can see that there is the first order term which is overwhelming the asymptotics, and you find that the probability that if I put 2 things together, that given I'm still alive at a late generation N, that my tree up to the first K generation looks like a given tree T is kind of the size biased distribution of the original one, where the size biasing comes from the population size at generation K. And that's the key of understanding the spine decomposition, because first of all, what is easy to understand that in the critical regime, surviving is an event of probability 0, has with n tending to infinity, very small probability. Surviving is independent for independent individuals, so that means the probability that 2 survive will be of even smaller order, so it's clear that there must be, if there is a spine to infinity, there's only 1 and not like a whole backbone of things. That is clear, and if you have this and you combine this with this formula and you apply this formula, for example, for the root, then it means that the root has a size bias distribution of children. And then among the first generation, there's exactly 1, which goes all the way to infinity, and the other just normal ones. You can collect everything in a statement which was first stated by Kesten in 1986, namely that under the probability measure, which belongs to the tree conditioned on survival, T has a single line of descent. And moreover, the number of children in that tree on the vertices which lie on that infinite line of descent are independent, they are IID with a size biased offspring distribution. That's what one can, I guess, easily understand. So far for conditioning, here a summary what we already have shown you. If we have the Poisson distribution, we have this feature, there's the size biased Poisson distribution, is just 1 plus the Poisson distribution. And if you use the 1 for the spine, which goes all the way to infinity, then you know that Poisson number of Poisson trees is branching off, but it's the same as 1 Poisson tree branching off in each of the things. And that's why you get this picture. And that's a crucial one because that will be one of the typical local limits we expect. Okay, that was part 1. Are there questions so far for conditioning? Yeah? I try to listen anyway. Yeah. I sorry, I don't understand the noises. A mic would be good, yeah.
Yeah, so in Keston's theorem, I'm saying that the probability that there are L plus 1 children, that is L plus 1 times the probability that your original distribution has value L plus 1. But for this to be a probability distribution, the expected number of children has to be equal to 1.
I phrased this for the critical tree, where the expected number of children is 1.
Okay.
So that this is a probability distribution. I agree. Did everybody got this question? I wrote down a distribution, and it's indeed the probability distribution only if the expected number of offspring is 1, which is the critical regime, which I didn't write explicitly, but I would like to have. Because we are mostly interested in Poisson 1, or at least intensity should have mean 1. Good. So are there more questions on conditioning? So if not, then I would switch topics now and come to electrical networks and random walks. And let me start very simple. The random walk, yeah? The first conditioning was because we had this statement that if I have the complete graph and I take the uniform spanning tree, I claim it's the uniform tree, and I claim that it's the same as a Poisson tree conditioned on having offspring distribution n. So now I made it more precise.
They would use that first exploratory walk itself, construct this spanning tree.
No, it will be just when tomorrow Ellie will present a proof of this very new result from Nachmias and Paris. She will use a lot of these facts. No, we will take them then for granted. She will also repeat it, but then you have seen once a little bit what is behind the story and why it is like this. Okay, the second one, I'm just collecting tools for in more detail, which usually you see only very short. So the second one is the random walk on graphs and electrical networks. We know that random walks have a lot, connections with uniform spanning trees. If I say I'm looking at a random walk on a given finite connected graph, then I also always mean a Markov chain on G, where I jump from one vertex X to a neighboring vertex X, so they have to build an edge with a probability, equal probability, 1 over the degree of that vertex. And it's also clear that this one is reversible, and reversible measures are up to a constant factor, the degree measure. And it's very easy to check, because if you multiply such an expression with the degree, then you get something which is symmetric in X and Y, so you can also interchange the variables X and Y. And for those are more in statistics, we have seen yesterday it was called a detailed balance equation, but it's precisely the same. And we always, when we have a Markov chain, we can talk about a Markovian generator, which in the finite case, it's very simple. But anyway, it captures all the dynamic. I would like to denote it, as usual, by the discrete Laplacian. The Laplacian takes a function f and maps it to another function. And this is given by taking the expected value of f of x1, which is the Markov chain after one step, and compares this with f of the initial value. And if you write whatever I have said before, you get this expression, you sum over all the neighboring vertices of y of x. This is the transition probability, 1 over the degree, and then the changes are you jump from x to y. Okay, so as I said, random walks are linked to uniform spanning trees by this formula, which we have seen now twice in January and yesterday. This is the probability that a particular edge from the graph belongs to the uniform spanning tree equals 1 over the degree of x times the probability, if I start in x, that I see the other end of that edge before I actually return to x. No? We have seen yesterday that it can be read off immediately from Wilson algorithm. So we have a proof of this formula. If you would like to use this in order to calculate these probabilities, then you can, of course, do this. This is all very elementary. No, here's a very small example. If you start in the root and you would like to know that you hit x1 before you return to the root, then you go one step with probability 1/3, you are here, and then you know you have met x1 before you return to row. With the remaining probability, you go to one of these points. Since the situation is symmetric, then it's 2/3 times the probability you start in x2 that you hit x1 before you hit the root. If you do it one more time for this expression, then you can either go down to the root, game is over, you have not seen x1 before you return to row, or you go up and see y. This happens with probability 1/2, so therefore 2/3 times 1/2 is 1/3. And now you are the probability starting in y that you hit x1 before you hit row, and you can do this one more time. Now you either go with probability 1/3 here, and you have found x1, or you go down here, and this gives you this equation. And what you see here are two equations, this one and the last one, which involve two quantities. That means you can solve it. And what you find is that the probability that if I start in the root, that I hit x1 before I return to row is precisely 1/2 in that simple example. And that means, according to our formula, that the edge from row to x1 will belong to the spanning tree of this graph is 2/3. No? And that's one tool you can do. Sometimes you can do this if you have a lot of symmetries, but mostly that's not what you want to do. You would like to have a more sophisticated tools which give you representation for this formula. It will be in terms of what is called the effective resistance. And you would also like to have these kind of tools, because very often you will not be able to calculate anything precisely, but you would like to get bounds, upper and lower bounds, to can study the asymptotics. And this is what I would like to introduce you for those of you who are not so familiar with electrical networks. No? So the basic idea, it's called electrical network because you can think about really a resistance network. You have your vertices, 1, 2, and so on, which are the nodes at which an engineer would measure the voltage. You have in between these edges, which you can think of resistors. And sometimes you also put a battery on this, then you impose some voltage here, or you ground it somewhere, then you have here a sink. So this is how these networks look like. And the first thing to define is a current flow. This is what they see, that along these edges a flow is flowing, and the flow always has a sign, so it makes a difference whether the electrons flow from 4 to 3 or the other way around. And therefore the current flow is a map, which is a map from ordered edges to R, which is defined anti-symmetric. And you say that there is no flow between 2 points if they are not connected by a wire or by an edge. And you have gradient flows. These are particular current flows, namely those which are of the form that I is the gradient of some other function phi. Usually we call this function phi a potential. And I define the gradient here. That's nothing else than this difference operator, phi of y minus phi of x. And of course, only if y is a neighbor of x. Otherwise, it's 0. Okay, there's one little bit quantity to introduce, but not more. And this is the notion of divergence. So the divergence of a flow is defined to you sum over all the current flows from x to a neighbor of x. And you have, if I write little diff, then it's just the density with respect to the reversible measure. So then it's capital diff I of x divided by the degree of x. And the first formula, which is very well known in differential geometry, is that the divergence of the gradient equals the Laplacian. And here, there's nothing to check. That's just in plugging the definition and see that these two things are the same. But it makes me easier not to write too much in the future slides. So then there are Kirchhoff's law. This is physics. No? This is what is described for how the flow is flowing in such a network. And the first thing is the knot law, which holds, which is for any vertex or knot, where there is no external current flow coming in or out. Then you have whatever flows into that knot has to flow out, which means that divergence of I at that point has to be 0. And then there's the cycle law, and the cycle law say if I have a cycle in the graph from x0 to x1 and so on to xn, then if I sum over all the flows, then I get 0. And this last one is a consistency condition, which makes sure that if such a cycle law holds, then E is a gradient flow. That means E is always of the form that it's the gradient of some function f, which we usually call potential. And also one can easily check that such a function f is uniquely determined by an additive constant. And if you want to prove it, you just take your favorite vertex, you put f of x0, 0, then you look at the neighbor of x, there might be several, and for each of the neighbors, you put f of y, f of x plus the current. No? And you do this inductively. If you have done this for a subset A, then you take one vertex y from the boundary, which does not belong to A, but is connected to a vertex in A, and you do the same approach. And then the circle law will just tell you that you don't run into any contradictions in doing so. Okay, so of course, the whole thing will be only interesting if in the end we impose some potential or some current, because otherwise there's nothing which will flow. And we do this as follows. We fix a non-empty set D of vertices. We impose the potential F0 on the complement. And then we allow currents to flow on D according to Kirchhoff's law. These two, the knot and the circle law. And then if I is the current flow, which must be of gradient form, then we know that the divergence of the gradient of F is 0. And that means that by conservation of current, that's the first law, the knot law, we know that this one is 0, but we also know that the divergence of the gradient is just a Laplacian. So that means that the solution of the function f, what we see will solve the Dirichlet problem. It will have the Laplacian f is 0 on D, and you have boundary conditions f0. Okay, and that means that my function f, which is the solution, is a harmonic function, because usually one defines a harmonic function on D as the unique solution of this, a harmonic function on D as just satisfying that the Laplacian of f is 0 on D. So from what we have learned, that's a classical statement that harmonic functions are uniquely determined. Prove this with the help of maximum principle. Let me do the shortcut and just say that harmonic functions on D must be the unique solutions of the corresponding Dirichlet problem. And on the other way around, to get the way back, that if f solves the above Dirichlet problem, then I, being the gradient of f, satisfies Kirchhoff's laws. Then we have found the current flow. Okay, so we are now approaching the notion of an effective resistance by taking our favorite harmonic function. Now we have seen these functions in the calculations we did, with hitting one point before the other. So let's introduce the function phi as to be the probability that you hit you have two fixed points, x and y, that you hit y before you hit x. No? And that's a function in the initial value z. So this is harmonic, can be easily checked by one-step probability distributions, and it has the property harmonic only on all points other than these 2 points, and on these 2 points you know the value, because you know that if I start in y, then I will hit y before I hit x with probability 1, and contrary, if I start in x, then I cannot hit y before I hit x. So I define the effective resistance as 1 over the divergence of the gradient of this particular potential phi in x. And if I do so, then it's just, again, basic manipulation of terms, that the effective resistance is nothing else than the term we had appeared for the probability that an edge belongs to the uniform spanning tree. And this is the way Kirchhoff, in his almost 200-year-old paper, formulated this probability. He expressed it through the effective resistance. So what we want is we want to calculate the effective resistance, and in cases where we cannot do so, which we often cannot do so, at least give upper and lower bounds. Before I go there, let me give you some consequences. First consequence is Foster's theorem. If I take the effective resistance and I sum over all the edges, x, y in the graph, then I get the number of vertices minus 1. That's something we will use in our calculations. And the reason it's basically that you can read such a probability as the expected value of the indicator that E belongs to the uniform spanning tree. And if I sum over all the edges, I get just the number of edges in the uniform spanning tree, which is always the number of vertices minus 1. That's the shortest proof I know of Foster's theorem. Yes. And there is something which might become of interest in a later stage of the project, because in the first one, we always want the Poisson tree as the local limit, because we would like to be in a situation where we are asymptotically independent, not for the edges to appear, but of course, later it can also be interested to have to introduce some dependencies, and by not letting the degrees go to infinity. And there is a generalization of Kirchhoff's theorem. You probably know how to do this, even though I didn't write it on the slide, because we have all learned yesterday about the spatial Markov property. We know what happens if I condition an edge to be present or an edge not to be present. And I again look for the uniform spanning tree, but unfortunately in a different graph, because the graph is changing due to the conditioning. So here's another way to express such a joint distribution by saying that there is a symmetric function h on pairs of edges, such that I can express this kind of joint distribution by the determinant of the matrix which I built from that symmetric function. And if I want to understand what such a theory means, it's not very explicit, I agree. But there are some things to learn about. And this is if I plug in just a one-dimensional distribution, R being 1, then I know that H, then this matrix is just H of EE. That must be the effective resistance. We have already proven this. And if I plug in 2 of them, then I see this is the determinant. And if I put everything according to H of EF and use that H of EE is the effective resistance, then I see some expression like this. So first, I'm only able to tell you a few slides later that this is always well defined because you have negative correlation. And second, what you can see that H depends only on the one-dimensional and the two-dimensional distribution of this thing. So if we have to do calculations, we mostly have to understand just the probability that two edges are there at the same time. Unfortunately, there's also a sign we have to deal with. That's a different story. And apparently, this kind of transfer current theorem has other nicer representations where one knows more about the function h if the graph has certain symmetries. So that might be a tool to study things, no, if we have certain symmetries later on. Okay, that was the heaviest of all the slides. We come back. And I told you that we want not only to calculate the resistance, but we would all like to bound it. No, we would find upper and lower bounds. So because it's usually more promising that we get something out of it. And this you can do because you can represent the effective resistance by two variational problems involving minima and maxima. And that's quite cool. And I start with the one which comes from the energy form. Let me take the finite connected graph and two functions. The energy of E and F is defined as a half the sum over all the vertices, x and y and v. And then I have here twice the gradient or this differential operator. And I did a mistake here. That's a mistake. This should be really x and y which are connected by an edge. No? So that here is actually what you read here is the sum over gradient f gradient g. But anyway, usually the way you form such an energy form is that you take the Markovian generator, and instead of looking at the Markovian generator and gain all the information you want about your Markov process, you do a weak evaluation by integrating against the test function g, and you take the inner scalar product with respect to the reversible measure you have in mind. And if you do so, and you remember that the gradient is diff of the, that the Laplacian is diff of the gradient, you get also this kind of form for the energy that you have. So I think the energy up to that here should be that x is a neighbor of y in the summation. It's a nice and easy thing to understand. And here is the relation to the resistance. We take a domain for this operator by taking all the functions which are 1 on y and 0 on x. If we do so, we define the capacity as the infimum over the energy over all these functions f, which have these two boundary conditions, 0 in x and 1 in y. And what we can then prove, what we find is that the resistance, which you have defined earlier, is nothing else than 1 over the capacity. And in order to prove such a statement, which is quite helpful, because it allows you to get lower bounds for the resistance, no? Because for a lower bound, you just have to take any function f which satisfies these two boundary conditions and plug it in and see what you get. You get a lower bound because you get an upper bound for the infimum, but because of the inverse, it's a lower bound for the resistance. So if you want to prove this, classical theory tells you that such variational problems have a unique solution and that the minimizer is always harmonic on V without x and y. And we know one harmonic function which has precisely these boundary conditions, and this is our function phi of z, probability that starting in z you hit y before you hit x. So you know the minimizer. You just have to plug it in. And sometimes it's difficult to calculate this, but not in this situation, because I told you that the energy form usually is minus the generator, this Laplacian applied to this function times this function. And now we remember that the function phi is harmonic outside x and y, so the Laplacian is 0 except in 2 points. So the whole inner product has only 2 terms. But here you have the probability with a starting point, and you know that if I start in x, this probability is 0. So what remains from the whole inner product? Just one term, namely the term with y. So here is the Laplacian, the starting point is y to hit y before x, which and I have here a 1 for phi of y is 1, and then it's the inner product with respect to this measure. This is the degree measure which we are taking in this setup. Okay, then I use that the Laplacian is minus divergence little diff gradient, but if I have here a degree and I put it in, then it's capital diff gradient, and this is by definition just 1 over the resistance, the way we have defined it before. So this tells us why the resistance is comes from this variational problem. Okay, you can use this variational problem to get a lot of other rules. Namely, you know what happens, you have some monotonicity if you manipulate and simplify your graph. And if the two operations I have in mind are the one which already appeared in the spatial Markov property. This is just taking away an edge or taking one edge and identifying the two endpoints. The first operation, it's called shortening. Now you're collapsing the set to a single point. Second operation is called cutting. You just take away the edge. So for the first one, collapsing the set to a single point, that means in your variational problem, you have another constraint, namely that the value on the one point is the same as the value of the other point. So you take the infimum over less functions, you get a larger value, the inverse will be shorter, so therefore the shortenings always decrease the effective resistance. For the taking away an edge, you have to think that if I am looking here at all these sums, I just have one sum and less. And if I have one sum and less, the functional I would like to optimize gets smaller, and that's why the capacity gets smaller and the resistance gets larger. So cuts always increase the resistance. And one other consequence one can do by the spatial Markov property is to convince you of this negative correlation, because if I calculate the joint distribution that E and F are in the uniform spanning tree, I can of course condition on the event that E is in the uniform spanning tree. And then remember that if I condition that E is in the uniform spanning tree, I have to collapse E to one point. No? And then you have, instead of the condition probability, because the collapsing, the shortening, the collapsing is shorter than if I would not collapse, no, I get here the smaller equal sign for this, which gives the negative correlation that follows from variational problem. Okay, there's one thing to notice, might not be that relevant in the moment, but it's very good for the understanding, is that the effective resistance you get from this variational problem satisfies the axioms of a metric. So you can use it as a distance. And that's a nice thing to think about, because if I have my network and I'm taking away one edge and I would like to learn about the distance between these 2 points, then they're now a bit further away. Because if I have Bangalore and I block a street, no, it might take much longer to go from here to here. And the same is with the collapsing. No, they become closer. So if you have always this idea that's also a distance, it's very good in understanding stuff. And it follows, and that's why I presented at that point, you can read it off immediately from the variational problem, the form I gave you. And because I said from the variational problem with the energy, you get a lower bound for the resistance, and you also want sometimes an upper bound to see whether your bounds are actually nice. I give you another variational problem, and this time it is in terms of current flows. So it works as follows. I start with my finite connected graph. I have two vertices. I'm taking the degree distribution. I define the domain again. This time I call it calligraphic I, X, Y as all the current flows, which have the property that the outside X and Y are divergence free. And I wanted the diff of I of X equals 1. So here I do a normalization. I want only flows of what we call the strength 1 by putting diff of I of X, forcing it to be 1. I have my bilinear functional. It's this time a function which takes two current flows. It's a half the sum over X, the sum over all Y, which are neighbored with X. Here is the flow I from X to Y times the flow J from X to Y. That's the functional we want to optimize. And what comes out and what is known as Thompson's principle is that the effective resistance is the infimum over this functional. So we are looking for the best flow of strength 1, and the value which comes out gives you the resistance. And because everything that's finite here, the variational problem has a unique solution, and minimizer it's also attained. And one can prove by characterization of minimizer, I won't have the time to do this now, is one knows what is the minimizer. It's nothing else than the effective resistance times the probability that I start in this argument Z of hitting the point Y before I hit X. And this time you can even plug it in. If this is your current which minimizes this, you get immediately This is just a constant factor which you can take out. You will take out it quadratically, but you know that if I put a gradient here and multiply with a gradient, if I evaluate this functional, I will just get another factor of 1 over the resistance. So in the end, I get the resistance itself. Okay, and I'm not making it harder, I'm making it easier. I just want to remind you that you all know from high school physics these rules, what you do with series law and parallel law. If you can always simplify these things by, if I have two of these things behind each other, think of it as a single resistor where you add up the resistances, and you can put several like parallel in the way I put here, and for two of them or even for more of them, it will always be the harmonic average. It's 1 over the sum of all the inverse of this one. And these rules, I won't have the time, but it's not hard to see that they follow immediately from the formulation of this variational problem. Because all you need to do is you just have to see that in such a network and in such a network, you get the same resistance between the 2 points. And if you have a flow for one of them, here's just one line. There's only one possible flow. Here, no, here, in this one, you had one line, you had one possible flow. Here you would have 2 ways to go, and then you see the minimum is just if you divide the flow equally, and if you do the mass, then you see what comes out will be just the same as if we would have just one resistor with this harmonic measure. And the other one also comes from that variational principle. You can think about it. And last but not least, because it appears in what Ellie is proving us tomorrow, is a lower bound for the effective resistance, which does not come from any of these variational problems directly, but it has a different reason, namely in any network, you can lower bound the resistance, the effective resistance between X and Y, which I reminded you is actually more a metric, no? Than a local quantity. By a local quantity, namely by the sum of 1 over the degree of X plus 1 over the degree of Y. And the reason to do so, it's kind of illustrated here. You know from X, you have degree of X edges going out, or flow flowing out, and Y, the flow is flowing in, and you have degree of Y edges, and inside you don't know what happens, but you can always decrease it, no, by the network reduction, by just identifying all the points to 1 point. And then you have the series law here, the series law here, and both, no, one behind the other, you get this expression for this one. And this holds in all the networks. It's often not good, but it is good in some situations, namely, it's near optimal when the missing part here is very well connected. Like Erdős-Rényi with a high sink or something like this, then this is usually not even more sparse. Erdős-Rényi do this for us. This is a very good bound, which is used in that topic. And I think I stop here. I was quite a lot.
Well, thank you, Anita. Questions? There's a nice little booklet by Doyle and Snell.
Yep.
It's called the Keras Monographs. And it talks about lots of intuition behind what you are doing. It doesn't so much talk about variational principles in great detail, but it's a lovely little book so if you want to learn more about what's going on, this is good. Doyle and Snell. We can you can no doubt find it. Okay. Thank you, Anita. We'll have a short coffee break.